Urgent. Look at your phone and you'll see a blue dot telling you exactly where you are. But that dot is a facade. GPS controls every modern utility, yet it can be hijacked by a $50 transmitter bought online. Global financial transactions, stock trades, and power grids rely on GPS for ultra-precise atomic timestamping to keep their systems synchronized. Without that pulse, the internal clocks of the global economy begin to drift. This creates a precarious flaw. The entire modern world depends on incredibly weak radio signals beamed from satellites 12,000 miles in space. Foreign adversaries and rogue actors no longer treat GPS jamming as a rare experiment. It is now a baseline tactic used to blind planes and ships in active transit zones. We built a global economy that requires a constant, uninterrupted connection to a fragile space network. It is a single point of failure society can no longer afford. The military is responding with a strategic shift. They are moving away from space-based reliance and toward terrestrial navigation systems that are completely immune to signal disruption. The Pentagon is currently investing $200 million into Project Farseer to rapidly fund these terrestrial alternatives and move them into the field. Military leadership has realized they can no longer look up for navigation. This forces a strategic pivot. To find our way, we must now learn to read the Earth itself. The solution is quantum sensing. Instead of receiving a signal from a satellite, these sensors measure the immutable physical properties of the planet to determine their exact location. The first method is magnetometry. The Earth's magnetic field isn't uniform. It is full of localized anomalies, creating a unique geographic fingerprint. These magnetic signals are impossible to hide. Because they are a property of the planet's core, they cannot be jammed by hostile forces. The second method utilizes gravity, specifically a process called gravimetry. By measuring dense underground structures and minute shifts in gravity, these sensors calculate location based on mass and subsurface geology. These systems are maturing out of the laboratory and are already being integrated into defense and aviation platforms for field testing. By converting the planet's fundamental physics into a map, quantum sensing makes the environment itself an unhackable navigation network. The third pillar is time. Next-generation atomic clocks are being miniaturized to maintain ultra-precise time internally, severing the need for external synchronization. This internal timekeeping insulates financial and logistical systems from desynchronization attacks, ensuring the pulse of the network remains steady, even if external signals are cut. Commercial adoption is following the military's lead. The UK government recently awarded £14 million to push this technology out of the defense sector and into public use. One major use case is navigating trains through the London Underground. It is a perfectly GPS-denied environment, where traditional navigation simply fails. As researchers miniaturize these systems into chip-scale sensors, the technology is following the same trajectory as the original GPS, moving from bulky military racks to the integrated circuits that will eventually power our mobile hardware. But there is a bottleneck. The industry is facing a severe quantum cryptographic imperative, and it currently lacks the human capital to scale this rollout. Many people assume that participating in this sector requires a PhD in theoretical physics. Today, that assumption is simply no longer true. The high-demand role is the quantum-aware engineer. This is a professional class tasked with bridging the gap between new quantum hardware and legacy systems. The true roadblock isn't the physics, it is a lack of classical engineering talent capable of integrating these sensors into existing infrastructure. Immediate roles are opening for post-quantum cryptography migration engineers and specialized software developers who can build the management layers for these sensors. There is an urgent need for network specialists to ensure these unjammable signals can be successfully integrated into the platforms we use every day. The market for these technologies is projected to scale from $100 million to over $3 billion by 2030, mirroring the semiconductor industry. This represents a lucrative career path for multidisciplinary talent ready to step up and learn the basics of quantum-safe systems. The transition to navigation based on the planet's own physical signals is underway, but building that bridge requires an entirely new workforce. Thanks for watching, and look for my upcoming book for a deeper look at your role in this shift.